All right, guys, this is last section of chapter 4. It's on metallic bonding, really short, and then intermolecular forces, which are a big part of how molecules will behave and their properties. So metallic bonding really focuses on this portion here. Really, that's why it's so short, because there is just not much interaction. So metallic bonding is obviously a metal. So in metals, you have these free electrons, and they're called a sea of electrons, and they freely move. So the ion itself is positive, with these electrons moving freely, and thus you have conductivity. So they use their valence electrons that move freely, either 2 or 3 or 1 electron, and they form a current. So you can see the more protons and free electrons you have, the stronger the metallic bond. So you're looking at more positivity, more negativity can create a stronger metallic bond. So here are a few things property-wise. The outermost electrons, the one they're valence, are held together through the positive charge proton. These free electrons can rapidly respond to electronic fields, since they're good conductors of electricity. They produce a lot amount of kinetic energy. That's why they're good conductors of heat. And the atoms themselves are hard, but they can slip through and be pressed. That's why they can be into shapes and into wires, into tools. So that's why the metallic bonding is the basics of our civilization, ever since back into the Bronze Age. Some other properties that you should know. Again, they're melded together between the positive cation and the electrons that are negative. They have high melting points and boiling points. They conduct electricity because the delocalized electrons are freely to move. They conduct heat because of the kinetic energy of the delocalized electrons, and they be drawn into wire because of the individual atoms are held strongly, but they can slip through and generate a different flexibility, malleable and ductile. All right, intermolecular bonding. So this is the key aspect to this notes. So we have your ionic, covalent, metallic bonding. So really this focuses on the ionic and covalent, specifically the covalent ones. You have intermolecular forces. These are the forces that hold the molecules together, not the bond, but the force that holds molecules together. So in ionic bonding, you have an ion-ion force. That strictly is the positive and negative charge atoms, and it's very strong. That's why you have high boiling points and high melting points. It's one of the strongest intermolecular forces, ion-ion. And then in covalent bonding, you have nonpolar substances like gasoline, carbon dioxide, nitrogen. These are all nonpolar substances. They're held together through what we call van der Waals forces, or VDW forces, sometimes also known as London dispersion forces. So if it's nonpolar, it's always going to be VDW as the main force. Everything has VDW forces, but they're not the lone. In nonpolar, that's this lone force that's holding it together. And then in non-polar substances, you have what we call dipole-dipole forces, and that is the positive and negative charge of a molecule attracted to the other positive and negative charge molecule. So you can see here the negative chlorine is attracted to the positive hydrogen. And then within dipole-dipole, you have specifically called hydrogen bonding, which is strictly just H with O, like water, H with N, like ammonia, or H with F, like hydrofluoric acid, or hydrogen fluoride. So those are 4 forces that we're going to talk about. Strictly, really the big difference is knowing if it's polar or nonpolar and how it fits in the intermolecular force. Metallic has no force. All right. So you can see the bond strength. Ionic bonding is the ion-ion is extremely high. The hydrogen bonding is next, and then the permanent dipole-dipole is second to last, and the van der Waals forces is the weakest with a very low bond strength. So the ability to attract a bond pair electrons towards itself is electronegativity. So how much negativity can it attract? So fluorine is the most electronegative atom. You see here at 4.0. And then everything basically from here goes down, with some exceptions like hydrogen. It's slightly higher than boron, or actually, never mind. That is, that's right about right. Here, the metals have a little bit higher electronegativity than some, but strictly, if it has, the closer you are to fluorine, the stronger the electronegativity. So as you increase electronegativity, you increase the atom's attraction for electrons. As you move right across the periodic table, it increases towards fluorine, and as you go up towards fluorine, it increases. So fluorine is the key. So everything that is based on electronegativity should be referenced through fluorine. You can see the halogens, bromine being the weakest, with fluorine being the greatest. All right, so polarity of molecules. This helps you determine the intermolecular force. When you have similar electronegativities, that means the electrons are sharing equally. They're going to be nonpolar. Because one atom's not pulling the electrons more than the other. So if they're very similar, it's going to be a nonpolar substance. Large differences have a electronegativity, have a polar bond. Okay, so one atom is stronger than the other. And then the greater the difference, the higher, so 2 or higher, is an ionic bond. So that's strictly going to be a metal and a non-metal. So there is a range. You can see here the nonpolar substances, the difference between electronegativities is very small, 0 to 0.4. Then if you have a polar covalent bond, it's between 0.4 and 2. And then the ionic bond is between 2 and 4. Okay. All right, dipole-dipole force. So dipole-dipole has electronegativity. One is greater than the other. So in this case, hydrogen is smaller than chlorine. Chlorine is a more electronegative atom. So it has more partial negative, and that's what that little symbol is. It's a lowercase delta. It means partial negativity. And this is partial positive for hydrogen. Kind of, you can use it like a ladle. It makes like a ladle. You can use that as your partial sign. So it kind of looks like a little soup ladle. So 2 atoms are partially charged. One is more electronegative than the other. The hydrogen is more positive. The negative is more chlorine is more negative. So it has a polar force. And since it's asymmetric, meaning one is stronger than the other, and it's not pulling in the same direction. So if you look at it and split it up in half, lengthwise and horizontal and vertical, you'll see it's not symmetric. So the intermolecular force here would be dipole-dipole because it's a polar substance, and it's not symmetric, asymmetric. The degree of polarity is measured by the dipole moment. So stronger the dipole, the more polar the substance is. So you can see here, if I were to split this in half, this side it's unbalanced. So, and if I go horizontal, again, this would be balanced. They're both similar on both sides, but the vertical is not balanced. You can see more red on one side and more blue on the other. So horizontally it's fine, but vertically it's not balanced. So that's why it's polar. Okay, you can have dipole moments, but be nonpolar. So you still have a big difference in electronegativity to have a dipole moment, but the dipole moments are symmetric then. They cancel each other out. It's kind of like having two strong people or two weak people pulling in the same opposite directions in the tug of war. It's not going to go anywhere because they're equally the same, and since they're equally balanced out, they cancel each other out. So here you have carbon tetrachloride. Even though chlorine is more electronegative than carbon, they all are pulling in the same force. So it's a nonpolar substance. So it has a polar dipole moment, but they're all the same moments and they're all equally pulling. They cancel each other out. So the net is 0, so it's nonpolar. So carbon chlorine has a difference between electronegativity, 0.5, but it's symmetric, therefore it's nonpolar, and it has a intermolecular force of van der Waals forces, VDW. Okay. Again, now if we change this, take one chlorine out and replace it with a hydrogen, now it's not all equal. It's not symmetric. So you now have a polar substance. So trichloromethane is polar because there is an unequal balance in polarity and dipole moment, where in tetrachloromethane or carbon tetrachloride, you have all equally the same, pulling equally, and it's nonpolar. All right, permanent dipole moments occur in polar substances. So look at acetone. Acetone has a partial positive carbon, and oxygen is more electronegative, so it's partially negative. So you show a partial negative on the O and a partial positive on the carbon, and therefore it's going to go towards the oxygen. And if I split this in half, yes, if I go vertical, it's equal on both sides. It's symmetric. But if I go horizontal, it's not symmetric. You have oxygen on one side and carbons on the other. So this would be symmetric that way, asymmetric with the blue. So since it's asymmetric on at least one way, it's going to be polar. All right, let's look at carbon monoxide and nitrogen. So what is similar about these two molecules? They both have triple bonds, but they're different atoms. So they have the same number of electrons. Carbon has 6, oxygen has 8, that's 14, nitrogen has 7, so that's 19, or 14, sorry, 14 electrons. So why is one polar and the other is not? Oxygen is more electronegative than carbon, and nitrogen, there's no difference in electronegativity because it's diatomic, they're both the same, so it's 0 difference between the electronegativities. So since oxygen and carbon are different electronegativities, carbon monoxide would be polar and nitrogen would be nonpolar. So even though they have the same number of electrons, they're different dipole moments because of electronegativity. All right, van der Waals forces or London dispersion forces. So the main thing with VDW forces is that you have a temporary positive negative going back and forth. That's why they're not strong, because it's not permanent. So like in helium atom, some of the electrons will be on one side of the atom and some of the electrons will be on the other, and causes a partial or a temporary positive negative charge, and that's what will allow them to attract each other. But since it's temporary, it will break apart. That's why helium is a gas at room temperature, because of the temporary forces. So if you look at the chart here, you can see the noble gases. Their boiling points are increasing as you go down the periodic table. Helium is the lightest, where radon is the heaviest. So now why, if they all have VDW forces, why is one more than the other? It's all based on the number of electrons. So the more electrons you have, the stronger the VDW forces. That's because it allows more positive negativity going back and forth, compared to something that has the least amount of electrons. They'll have some partial negativity and temporary forces, but it will be very small. Where more electrons, you have more of those forces, and they can be a stronger bond or stronger hold force between each molecule. So if something has high VDW, it means it has more electrons. So how does VDW increase? Increased number of electrons and protons causes a stronger temporary dipole. And you can increase VDW forces by contact points, surface area. So if you have more surface area around a molecule, you'll have more contact points and thus a stronger force. Therefore, a higher boiling point and more energy to break the molecules apart from each other. So you look at helium and argon. Which one is going to have a stronger van der Waals force? More electrons, more protons. Okay, which ones have a higher melting point? So argon is going to have a stronger VDW force because it has more electrons, where helium only has 2, argon has 18. All right, here is an example of contact points. So they're both the same number of carbon, same number of hydrogen, same number of same formula, but you have different shape. Pentane is more linear, where 2,2-dimethylpropane is more horizontal and vertical. So which compound do you think has a higher boiling point and why? They have the same number of electrons, but pentane has a boiling point of 36, where the other one has a 10-degree boiling point. So the reason why is because it has more contact points. So more contact meaning higher VDW forces. You can also see the relationship with more van der Waals forces with the enthalpy of vaporization. You see it's increasing. And the boiling point is also increasing because of the number of electrons. So again, every property is based on these forces, which is based on the number of electrons. Okay, so higher number of enthalpy, higher increase of vaporization and higher boiling point is based on more electrons in that atom. All right, butane and propanone, sorry. Which compound do you think has a higher boiling point and why? So you can see butane looks symmetric, has just a carbon and hydrogen, where propanone has an oxygen containing in it. So you're going to expect propanone to be a stronger intermolecular force because it has a dipole-dipole permanent force, where in butane it only has a weak van der Waals forces. So it's a gas at room temperature, where propanone is a liquid at room temperature. They both have the same number of, or same mass. So that's not going to affect the number of electrons. It's based on the electronegativity of oxygen causing it to be polar. Therefore, it has a permanent dipole-dipole force. So butanone is at 0 and propanone is at 56. You need more energy to break propanone because of the stronger intermolecular force of dipole-dipole. All right, here is homework question on OneNote, or you get it through Teams. Determine if it's polar or nonpolar, and then explain your answer. Okay, so you have to see, they give you the shape, so you have to see if there's dipole moments, and if there's a symmetric or asymmetric shape to it. Question 11 is that bromine and iodine monochloride had the same number of electrons, but the boiling point of ICl is nearly 40 degrees higher than the boiling point of bromine. Explain this difference. So again, if they have the same number of electrons, you're not looking at VDW. You're looking at what force does bromine have and what force ICl has. And that's going to help you determine the difference in boiling point. All right, hydrogen bonding. So hydrogen is the strongest of the covalent molecules. It's only between H and F, H and O, and H and N. So basically, if it's polar and you have HF or HO or HN, you know it's going to be hydrogen bonding. So why is it only F, O, and N? You might have thought, like, hey, Stevenson, why is it only FON? Because it's not fun. Just kidding. FON, F-O-N, it's because of the atomic radius is so much smaller than the other elements in those groups. It allows it to have a stronger intermolecular force. So they specifically say hydrogen bonding because hydrogen is small. It's going to have a stronger hold from fluorine, oxygen, nitrogen because of the atomic radius of those. So you can see here we have ammonia. The hydrogen bond is occurring between the lone pair of nitrogen and the positivity of hydrogen, and that forms a hydrogen bond. You can see here also better direction. Also with water, the lone pair of oxygen allows a bond with H, and it happens twice because there's two lone pairs on oxygen. How does hydrogen bond affect boiling point? Hydrogen bonds are very strong, so you're going to have an increase in boiling points. That's why water has such a high boiling point compared to other atoms in that group. So if you're looking at the difference between H, HCl, HBr, and HI, you will see it actually dip. HF having the strongest, it dips at HCl, and then it increases as you go to HI. So why does from HCl to HI increase? So that means you have a stronger dipole-dipole force in HI compared to HBr. That's due to its size. of the atom Cl, Br, and H and I. All right, here is a third question. You have ammonia, phosphine, which was just found in Venus, arsenine, and stibine. Stibine, sorry. Explain the trend in the boiling points. So you should see it's basically the same idea, that it goes down and then back up. So explain why boiling point of ammonia does not follow this trend. So again, kind of the same idea with hydrogen bonding. So basically, A is explain the trend, what's happening between phosphine and stibine, and then explain why ammonia does not follow this trend. All right, so here are some enthalpy of vaporizations of group 6. Those are your water, sulfur, okay? So again, number of electrons is, there's a decrease after 20 because of hydrogen bonding, and then it slowly increases due to the amount of electrons present, their increase in forces. So predict the trend of this group. Hydrogen should be first, and then you should have H2S, H2SE, and then H2TE at the end. Okay, so again, it's just like the boiling points. Water is going to have the highest because of hydrogen bonding, and then there's a slow increase as you go down the periodic table because of the size of the atom, causing more van der Waals forces in these structures. All right, some other things about water that's so important and really important to our daily life. Surface tension and viscosity. So there's a high surface tension for water because of the hydrogen bonding, and water becomes less dense when ice. That's because it produces a rigid lattice and kind of stucks air in between those bonds. So when you form ice, it actually expands. So that's why things will explode in the freezer. The ice is actually expanding because it locks air in and causes a crystal lattice, and then there's nowhere to go, so it has to break the container. So that's the reason why that's why it expands, but also why ice is less dense than water, because little air pockets form in those crystals. All right, I know it's a little long, but it's important to understand the polarity and understand the three major forces. You have van der Waals, dipole-dipole, and hydrogen bonding. Ionic is easy because it's just ion-ion, but everything starts with understanding the electronegativity difference and symmetry and asymmetric molecules. So if it's symmetric all the way, you know it's going to be nonpolar. If there's any asymmetry, it's going to be polar. I don't know if that's a word, but asymmetric.